All right. Let's dive into this memory layers at scale paper.
Okay.
It tackles this problem that's been, nagging AI development for a while.
Yeah.
Like how to make models smarter.
Right.
But without, making them just ridiculously huge and computationally demanding.
Exactly. We're kind of hitting a wall with just adding more parameters.
Right.
It's just not efficient.
Yeah.
We need some new approaches, and this paper offers a really interesting one with these memory layers.
So I get the basic idea.
Okay.
It's like giving AI this external knowledge base to pull from. But how does that actually work in practice?
So imagine like this huge searchable table where each entry has a unique key associated with a specific value. And in this case, the keys represent those input queries or prompts.
Okay.
And the values hold the corresponding information or responses.
I see.
And the important thing here is that it's trainable.
Okay.
It's not just a static lookup. The model's actually learning these associations between the keys and values.
Interesting.
Which are represented as mathematical vectors.
Okay.
And it refines those relationships during training.
So it's not just like a dictionary.
Right. It's more dynamic.
The model is actually like learning how these pieces connect.
Exactly. And what's really cool is that it doesn't need complex computations every time it needs to access information. It's a direct lookup. Way more efficient than sifting through a dense model's parameters.
So the paper highlights several innovations within this framework. And one that caught my eye is product key lookup.
Yeah.
What is that, and why is it so important?
So think about searching through a massive library.
Okay.
Looking at each book individually would take forever.
Right.
Product key lookup solves this with this really clever indexing system.
Okay.
Instead of a linear search, it divides the keys into segments based on a product operation on their vector representations. So the model can quickly zero in on the relevant part of the memory instead of searching everything.
So it's like breaking down a huge library into smaller collections.
Exactly.
So you can find what you need much faster.
Right. And that's crucial when you're dealing with these massive memory layers.
At billions of parameters.
Yes.
And speaking of which, the paper talks about parallel memory. Is that about using multiple GPUs to handle that scale?
Exactly. It leverages the power of parallel processing to distribute that memory load. So you can store and retrieve information from these huge key value stores.
I see.
Otherwise, we'd be limited by a single GPU.
Right.
And couldn't have these massive memory layers.
Okay, so parallel memory is essential for that.
Yes.
Now, there's also shared memory mentioned.
Yeah.
Does that mean different layers in the model can access the same memory pool?
That's exactly right. It's a really smart way to maximize efficiency and keep things versatile instead of each layer having its own dedicated memory, which would be redundant and bloat the model.
Right.
They all tap into one central repository.
So like different departments sharing a knowledge base.
Exactly. Cool. So a single fact can be used by different parts of the model for different purposes.
Now, the paper also talks about these custom CUDA kernels.
Yes.
And memory access optimizations.
Right.
What can you tell us about those?
Well, this is where the theory meets the practical implementation.
Okay.
Dense models have been refined for decades to run well on the hardware we have. But memory layers are different.
Okay.
With their sparse activation patterns, they present new challenges.
I see.
So the researchers had to really dive deep into how the hardware works and optimize those memory access patterns.
Okay.
They even developed custom CUDA kernels.
Interesting.
To take advantage of those parallel processing capabilities of GPUs.
So it's like they're restructuring how computation works to fit memory layers.
Exactly.
And they got a pretty big speed boost, right?
Yeah. They reported up to a 6-fold increase in speed.
Wow.
In certain scenarios.
That's amazing.
But it's not just about speed.
Right.
There were stability issues during training with these huge memory layers.
Okay.
Think of it like trying to teach a class with millions of students.
Oh, wow.
It can get chaotic.
Yeah, definitely.
So they introduced a gating mechanism, like a traffic controller, to regulate the flow of information during training.
I see.
It prevents things from getting out of control by selectively allowing information to pass through.
Gotcha. So the model learns steadily
Exactly.
without being overwhelmed.
Right.
So they really thought about both the theoretical and practical aspects.
Yeah, they did a great job of that.
Which is key for moving this research out of the lab and into real-world use.
Absolutely. And these optimizations directly impacted the performance and capabilities of the models.
Okay, cool. But before we dive into the results,
Sure.
I think we should step back a bit. What do these memory layers and their implementation mean for AI development?
Right.
Are we like shifting how we build and train these intelligent systems?
That's a great question, and I think it's a perfect place to wrap up this first part of our deep dive.
Okay, sounds good.
We've laid the groundwork.
Yeah.
And when we come back, we can explore those results
Awesome.
and discuss what they might mean for the future of AI.
I'm excited to hear more.
Yeah, it's really fascinating stuff.
Stay tuned, everybody.
We'll be right back.
So before the break, we were getting into the technical side of these memory layers.
Yeah, all the innovations they had to make to implement them.
Right now, I want to talk about the results.
Okay.
What did they find when they actually put these models to the test?
Well, the results were really impressive.
Okay.
Significant improvements across a variety of tasks.
Interesting. So not just limited to one specific area?
Exactly. It wasn't confined to a narrow domain.
Okay.
They tested them on all kinds of benchmarks, like question answering, coding, and general knowledge assessments.
Okay.
And saw consistent performance boosts.
So it seems like memory layers can really enhance AI capabilities.
Yeah, it's not just about rote memorization.
Right. It's something more than that.
They're showing real potential.
Can you give us some specific examples of where these models really shined?
Sure. So one example is the natural questions benchmark.
Okay.
This one evaluates a model's ability to answer open-ended questions based on Wikipedia articles.
Sounds challenging.
It is, and the memory-augmented models did really well,
Right.
consistently outperforming dense models with comparable computational budgets.
So they were more efficient?
Yes, in some cases, they even beat models with twice the computational power.
Wow, that's amazing. It's not just about bigger models anymore.
Right. Using memory strategically can be much more effective.
Yeah, it seems like that's a key takeaway here.
Definitely. And the gains weren't just in question answering.
Okay, what else?
They also saw improvements on coding benchmarks,
Like what?
like human eval and MBPP. Memory-augmented models were better at generating accurate code.
So they were better at problem solving.
Yeah, it suggests they can handle logical reasoning and symbolic information manipulation.
That's huge for fields like software development or
Absolutely.
scientific research.
Right, if AI can reason and problem solve at a higher level, it opens up a lot of possibilities.
Okay, so we've talked about question answering and coding.
Yeah.
What about general knowledge?
They tested that too on a benchmark called MMLU.
MMLU, what is that?
It covers a wide range of topics.
Like what kind of topics?
Everything from science and history to literature and social sciences.
Wow, so really broad.
Yes, and once again, memory-augmented models outperformed dense models.
Interesting, so they showed a deeper and wider comprehension.
Exactly. They had a better grasp of the world in general.
It really does seem like we're moving beyond just cramming more data into these models.
Right.
It's about how they use the information.
Exactly. Finding ways for them to learn and use knowledge more like humans do.
Yeah, connecting the dots.
Right. Building on a foundation of facts.
Okay, so could memory layers be a key to unlocking this more human-like learning process?
Well, that's a fascinating question.
Yeah.
Current AI models are great at specific tasks, but they struggle with flexible and adaptive learning like we do.
Right, we're constantly learning and adapting to new information.
Exactly. And memory layers could provide a framework for AI to do the same.
So they could learn and adapt continuously.
That's the idea.
Wow, that would be a big breakthrough.
It would. And this idea of continual learning has been a challenge in AI.
Yeah, they tend to forget old information when they learn new things.
Right. That's the problem of catastrophic forgetting. But memory layers could potentially solve that.
Okay, so what would that look like in practice?
Well, imagine a self-driving car that learns from new road conditions in real time.
Okay.
Or a personal assistant that adapts to your changing needs and preferences.
Those are some compelling examples.
Yeah, and those are just a few possibilities.
But the paper also acknowledges there's still work to be done.
Of course, this is just the beginning.
Right. What are some of the challenges moving forward?
Well, one of the biggest ones is optimizing these models for real-world deployment.
Okay, so taking them from the lab to actual applications.
Right. The research shows great results in controlled settings,
Yeah.
but real-world applications are much more complex.
Okay, what kind of challenges are we talking about?
Things like efficient memory management and access when you're dealing with massive amounts of data and complex scenarios.
So bridging that gap between research and practical implementation.
Yeah, that's a key focus area.
Are there any other research directions you think are promising?
Absolutely. One area is exploring new ways to access and retrieve information from memory.
Okay.
The product key lookup method is great, but we can improve it.
Right.
Finding better ways to index, search, and retrieve from these massive memory stores.
That makes sense. It's all about efficiency.
Yeah, and speed.
Now, what about the type of information stored?
Right now, the focus is on factual knowledge. But what if we could store more abstract concepts?
Okay.
Relationships, procedural knowledge even.
That's a big jump.
It is, but imagine a memory layer that stores causal relationships, logical inferences, even emotional associations.
Wow.
AI could reason about why things happen,
Okay.
predict future outcomes, even interact with us on an emotional level.
That's getting into some deep philosophical territory.
It is. As AI gets more sophisticated, it raises more questions about the nature of intelligence itself.
Yeah, and consciousness.
Right. Are we blurring the lines between artificial and natural intelligence?
So memory layers are not just a technical advancement.
No, they're prompting us to rethink what AI is and can be.
Fascinating stuff. Well, we've covered a lot of ground here.
We have from the technical details to the philosophical implications.
But we're not done yet.
Right.
When we come back, we'll look at some specific examples and benchmarks that showcase just how powerful these memory-augmented models can be. Welcome back to the show.
Glad to be here.
Okay, so we've been talking about the architecture and the potential of these memory layers.
Yeah, laying the groundwork.
Yeah, now I want to see them in action.
Okay.
Let's look at some specific examples where these memory-augmented models really shine.
Sure. So one example that really stands out is their performance on the Trivia QA benchmark.
Trivia QA?
Yeah, it's designed to test a model's ability to answer those tough trivia questions.
Okay, so it needs both a lot of knowledge and the ability to connect the dots.
Exactly. It has to retrieve and synthesize information from various sources.
Did the memory-augmented models do well on this?
They did really well.
Okay.
They consistently outperformed traditional dense models.
Even bigger models?
Even models with significantly more parameters.
Interesting.
And what's really impressive is how well they could recall and integrate facts, even when the information was spread out or presented in a complicated way.
So they weren't just doing simple keyword matching.
Right. It was more than that.
They were understanding the relationships between different pieces of information.
Exactly. They were showing a deeper level of comprehension.
Which is crucial for real-world applications.
Absolutely. In the real world, knowledge is messy.
Yeah, it's not always neatly organized.
Right. We're constantly pulling from a web of interconnected knowledge.
And it seems like memory layers are helping AI to do the same.
That's the cool.
Which brings us back to that idea of continual learning.
Yeah.
If these models can keep integrating new information into their memory layers,
right,
always building on what they already know.
It opens up so many possibilities.
Yeah, exactly.
And it's not just about accumulating facts.
Okay, what else?
Imagine a memory layer that can store procedural knowledge.
Okay.
Algorithms, creative concepts even.
Wow. So AI could learn new skills.
Yes.
Solve new problems, even create art.
Potentially, yeah.
It's like we're giving them a toolbox and the ability to build their own tools.
I like that analogy.
It's not just about storing more information. It's about changing how AI learns and interacts with the world.
Exactly. It's a fundamental shift.
This research is really exciting.
It is.
But we also have to talk about the challenges.
Of course.
We've mentioned the technical hurdles, but what about the ethical considerations?
Right. As AI becomes more powerful, we have to be very careful.
Exactly. We're talking about systems that can learn and adapt on their own.
Yes.
How do we ensure they're used responsibly?
That's the big question. We need to consider bias, fairness, transparency, accountability.
Right. How do we make sure these memory layers contain accurate and unbiased information?
And how do we prevent them from being used for harm?
These are big questions.
They are, and they're not just for researchers to answer.
Right. This is a conversation for everyone, developers, policymakers, society as a whole.
We need to be proactive and thoughtful.
AI has immense potential.
It does.
But we have to make sure it benefits humanity.
Absolutely.
Well, this has been a fascinating deep dive.
I agree.
We've explored the technical side, the potential benefits, and the ethical challenges of memory layers.
It's a lot to think about.
It is, but it's clear that we're entering a new era of AI.
One where machines can learn, adapt, and maybe even think more like us.
It's exciting and a little bit daunting.
It is. But I'm optimistic.
Me too.
As long as we approach these advancements responsibly.
I think that's the key takeaway here.
It is.
So thank you for joining us on this deep dive into memory layers at scale.
It was a pleasure.
We hope this has sparked your curiosity and inspired you to learn more about this amazing field.
Keep exploring and keep questioning.
And we'll see you next time on The Deep Dive.
Bye, everyone.